can. Okay, so to go over the course outline again, so we've covered sort of the image enhancement and basic segmentation last time, where we covered the ROC curves, and we'll talk about that a little bit more today. And then we have the advanced segmentation, and then we move on to the next part of the course where it's really about analyzing these objects that we've segmented. And so how can we make meaningful statements about them in terms of shape and distribution and everything else? And then the statistics and reproducibility aspect. So how do you ensure that these analyses that you do, you'll get the same result every time, or if someone else tries to do it, that they'll get the same result too, and that the differences that you see are in fact relevant, so that they're meaningful for describing your sample and not just noise in your system. Then have sort of dynamic experiments, scaling up, and then the 2 guest lectures, which are still being finalized, but the high content screening looks like it will happen, and then the sort of deep learning, more advanced approaches will happen as well. And so there we'll go over sort of one of the contests that they have and how you make a solution using a deep learning approach, and sort of what the connection is between all of these methods that we've covered and this whole deep learning thing. I mean, I assume most of you have heard about this AlphaGo this week that was playing and beat a human, or the best human player in the world, and so understanding what kind of approaches this machine uses and how these techniques fit into that is quite important. So there's, again, quite a bit of literature and useful references, particularly for some of the more advanced topics that we won't really get into very much. You can read these to kind of understand more, particularly Markov random fields and active contours, which are very popular segmentation techniques that we'll just mention. And if you're interested in knowing more detail or the mathematical background, then I recommend looking into those and more. So in sort of the outline of what we're doing today, we have sort of the motivation and sort of why do we need more advanced segmentation techniques in the first place, and there's some videos for that. The second is sort of thresholding. So how can you do thresholding better? So when you have lots of different samples, how can you avoid having to pick this threshold value every time? Then looking at feature vectors a little bit and what sort of information they can provide to us, and how we can use that to assist in the whole segmentation process. And then this is kind of beyond that. Once you've done the initial segmentation, how you can improve it. And so last time we covered a bit of these morphological operations. We'll extend that with sort of contouring, and then we'll have this fuzzy models and component labeling aspects that we bring into it. So in terms of what we've covered last time, or the times before, the image acquisition and representation, so where the images come from, what sort of problems they have and how we try to fix it. The enhancement and noise reduction, so how we make the images look better. Understanding models, interpreting histograms, and then this idea of ground truth and ROC curves. We then sort of looked specifically at choosing a threshold, improving the segmentation, and sort of the volume, partial volume effect. And so when one of the cases where we see that segmentation really has a problem, or the standard threshold techniques have a problem, is where you're trying to sort of counteract inconsistent illumination. So in microscopy experiments or white light experiments, a lot of times the illumination isn't constant. And so some images will be very bright and some images will be much darker. And so that's sort of shown here. And if you try to use the same threshold for all of the images, you get very different results. And so if you're interested in the number of cells in your image and you're using a constant threshold, then you have a not particularly meaningful analysis. And we also see, if you look closely at this image, that the size of the cells actually changes as well, or the perceived size of the cells from this threshold changes as well, because that illumination, having a constant threshold subject to non-constant illumination, causes these values to change. Another place where this fails, and this is probably, again, in sort of the microscopy area, more interesting than in other imaging modalities, is when you're trying to find very, very small structures. And so this is an example where you have this bone sample, you have these large canals, and you have sort of these cells. And these cells are connected by tiny little channels. And the little channels are very difficult to see and are not very different in density from the bone around them. And so trying to find these little channels that are connecting the cells together is very difficult, but it's important for understanding sort of how the cells communicate, how nutrition is spread around through cells, how mechanosensation works, and these other processes. And so what sort of techniques can we use to try to recover these really tiny structures, or these structures that aren't very strongly differentiated? So clearly, if it's full of air and it's a large hole, segmentation will find this without any problem. But when it's these smaller holes and they aren't as differentiated, how can we start to find them? And then sort of another task is, looking at sort of the brain cortex image that we showed briefly last time. And so this is a phase contrast image where you see electron density. And if you try to sort of segment with intensity values, you get lots of different segmentations, but you don't get anything resembling sort of the region you'd want to get out of this image, which in this case is the cortex. And so what has been done typically is to manually sort of draw contours around this, which is very time consuming and not very reliable. And so how can you process images like this and segment out the regions that you're interested in? I think this. And then the last aspect is sort of looking at even more complicated scenes. And so this is a video of a car driving around. And there, you're not trying to quantify just the road. You want to know where the road is. You want to know where the trees are. You want to know where barriers are, if there's pedestrians walking around, if there's sky in the background or anything else. And so this requires, of course, a much more complicated form of segmentation so that you end up extracting the reasonable parts of the image, and if you just look at intensity, you won't get any meaningful information out of it. And so you need to include more information to try to get the relevant parts out of the image. So for the very first thing we'll cover is automated threshold selection. And so this is really applicable for the large number of samples or the changing illumination. And so what you can do here is you can choose a threshold value automatically. And so there's a number of different techniques which let you find, looking at the histogram, looking at the image, looking at features in the image, a threshold based on that rather than sort of a fixed value. And so the three different types of approaches that we have here are histogram-based methods. And so this is where we take the histogram that we covered last time and we try to find where a threshold would make sense based on this data. So one of them is sort of this intermodes method, and this is what you naturally do when you look at the histogram. And so it finds the two modes of the system, so these two most common values, these peaks, and then it finds the value, the minimum between them. And so if you have two clear peaks that are always in the same place or always more or less in the same place and same positions, then you can use a technique like that to automatically pick the threshold so that even if there's a shift, it will sort of follow along in the data. Of course, if the peaks are not clear or there's multiple different peaks, then this is a very unreliable technique because that will be subject, you don't know which two peaks it might end up picking. And if these intense or relative intensities change, then it could be switching to different features inside your image. There's other techniques like ISO data, which I think we cover in the next slide. The next one is image-based methods. And so these look at the statistics of the threshold images themselves rather than the histogram. And so it takes the entire image at threshold, applies a threshold to it, and then it estimates a factor like entropy or any number of other different parameters that you want to calculate and uses this to, and tries to minimize this value. Yeah?
What is meant by entropy?
That when you look in a small region or when you look in a region, what the different values appear inside it. And so you can choose a threshold so that the sort of variation, I guess, inside the regions is very small compared to the variation between the regions. And so this can also incorporate spatial position as well, so that you can say that things that are close together should be very similar in value. And so you want to make your threshold such that these groups stay together. The final sort of approach that falls into this category are really the results-based methods. And so this is where you search for a threshold based on what gives you the best results for what you're looking for. And so if you're trying to find cells, as we had in sort of this original example here, that if you know the average cell size is 200 microns, then you can adjust the threshold in each image until the average object size is 200 microns. That means that you can't use the size that you get out as sort of a useful study parameter anymore, because you've adjusted all of the values so that that's one of your outputs. But it means that you're always sort of finding the same sort of structures in your image. And these results-based methods typically require you to implement them manually. And so the histogram methods and image-based methods are available by default in sort of ImageJ and KNIME and sort of these other tools that we use. A lot of the result-based methods you'll have to do yourself, because it requires sort of information about what features you're interested in looking at. So for the histogram-based methods, if you take sort of a typical image of a bone slice, you can see that the values that we're looking at here are this calcification density. And so the brighter it is, the more calcium there is in a specific region. And that what we get a histogram out, and you see that sort of this is the air in the system. This is bone, and it gets from lower density to higher density, and there's probably some artifacts in the image as well. And we have to pick a threshold somewhere that distinguishes this from this, because those are sort of the two peaks of interest of the things that we're looking at. If we were trying to look for this calcified tissue here, where would we segment it? So these stripes that you see in the image like that and that.
Guess that the stripes fall into that second peak on the far left of the, maybe.
The far left?
Yeah, well, let's see, left of the page, left of the image. So with the, if you have a histogram,
Yeah.
You've got two peaks.
Yeah.
The big peak is probably the most dense structures. The big peak in center is
Yeah.
the most dense. And those other lines of a lighter color, I would first do some measurements to verify that their calcification level is probably in that second peak. And then you divide between the two peaks.
Yeah. So these structures. So the biggest peak here corresponds to what most of the image is made up of. So the size of the peak is the number of pixels that we have, or the area of the image that fills in that. And so this would say that sort of most of it is around 0.5. And these white structures, like you said, are sort of brighter in intensity, and how we can find them is then to choose a threshold here. So that if we're trying to differentiate between air and bone, then our threshold wants to be somewhere between those two peaks. And when we're trying to differentiate between really dense calcified material, or calcified cartilage, I think is what it is in that case, and normal bone, then the threshold would be rather on this side. And so that it's important when you do these segmentations that you have sort of some idea of where you expect the result to fall. Otherwise, when you do an automatic approach, it will always give you a threshold, but it may not be meaningful. I mean, the techniques that we talked, like Otsu and entropy-based, don't have any biological meaning. They just help you get to a value or a segmentation of your image that makes sense, or that mathematically works. And it doesn't have anything to do with the original problem or where your data came from. And so it's always important to do sort of a sanity check of 0 is no absorption or no calcium, that's probably air. 1 is complete calcium, so that's probably really dense. Bone isn't complete calcium. There's lots of other things in bone. And so this probably is bone. This is the really dense part of it. This is then the less dense part of it. And then this is air. And that what we see here, what do you think would be easier to distinguish between bone and air, or between bone and these really highly calcified regions? Yeah.
Bone and air is its own peak, and it's difficult, and you have to decide when your bone starts to become very dense.
Yeah, so we see no peak over here at all. And so it'll be very difficult to just kind of arbitrarily pick something and to say that that's these calcified tissues that we're interested in. It's possible. I mean, again, we can use these ROC curves and things like that to say this is what we know from histology or some other type of image, that this is calcified tissue or highly calcified cartilage. And then we can try to figure out what value of this matches that the best. But without having some other form of data or spending a lot of time tweaking it, it can be really difficult to differentiate between bone and very mineralized bone.
I would imagine in these cases, if you don't have the histological data, you could take some samples and take a look at what the values are. So in this image here, you recognize some structures you're interested in, you measure a few of them as a sample, and then you look where they are.
Yeah, you can do that. The problem with that is that you then introduce a lot of bias from yourself. And so we see in this image that we have edge enhancement, which isn't something we'll really cover in this course at all, but that causes these values to be much brighter than they normally would be. And so trying to say this is where the edge enhancement ends and this is where the calcified cartilage begins can be really arbitrary. And so if you can have, I mean, of course, if you don't have any other information, then you have to do it based on this. But if you have access to other types of data or other modalities or some sort of ground truth, that can make this task much, much easier. And we've actually seen papers before where they wrote about sort of this hypercalcification around the cells, which is edge enhancement. So there's actually not any more calcium around the cells if you look at it in detail with another technique. But because this imaging technique enhances differences and wasn't correct or perfectly compensated in the final image, people assumed that that meant the calcium density was higher. And so that's, of course, where you end up with problems when you interpret your data without having any correction or understanding. So now if we look at the histogram methods that we have, the first one is sort of this intermode where we take the point between the two modes in the histogram. And so the two modes are 0.5 and 0. And so that fits right here. And even if this peak shifts over a bit to the right or a bit to the left, that intermode value will sort of follow with it. The second is this Otsu method, which searches and minimizes the intra-class variance. And so that's once you've decided what the two groups are, what's the variance within the group? And what are the variance between the groups? And so if you can calculate that, you can try to minimize that factor. And this is then done in an iterative manner. And so you pick a threshold, you calculate these variances, and then you update the threshold and calculate it again and try to get to the minimum value between them. ISO data works similarly. So you have sort of the threshold is the average value in the image. So you take the max and the minimum and go in between. And then you sort of run this loop iteratively again, where the background is everything that's less than the threshold, the object is everything that's greater than the threshold, and the new threshold becomes the average value in the background plus the average value in the foreground divided by 2. And so that might appear to be the same as the average value in the image, and so you're done after one iteration. But that's only the case if your histogram is completely uniform. As soon as your histogram has some structure in it, then the sum, or the average of averages, isn't the same as the average of the entire image.
So on this histogram, where would a technique like that end up being? In the dead middle between the two, or if you keep iterating, where would you expect it to fall?
I think in this one it falls
Right in that hole.
more or less there. But it depends. I mean, it's hard to say just looking at it. Yeah.
Would it be like if we say that air does not absorb at all, or whatever this picture is
Mhm.
from, can we just say that 0 has to be air and everything else has to be null?
Right. But where does 0 stop being 0?
I mean,
So when we
say-
look at this value,
Good noise.
there's, I mean, if you zoom into this image, and you probably don't have that high of a resolution, so you can't see it very well. But if you take this image and you try to zoom into it, we can actually, it's probably much better to do it this way.
Most types of input techniques, there's going to be some distribution. You know, air should be 0. The noise and technique itself is going to have 0 plus 0.01, minus 0.01.
Thank you. I think I have this bone. Is there no better? Oh, there it is. So if we open this image, and we look at the values that we have in it, so this is 82. And so if we make the histogram that we have, it probably will look slightly different. So process as it is. So we have 0 to 255, just like we had 0 to 1 before. And you can see that there's sort of a peak close to 0 here. We can do the log scale so that you see it more clearly. So there is sort of a peak at the beginning there, but it's not perfectly narrow. There's some width that it has. And so at some point, this goes from being air to being bone, but it's not completely clear where this happens. And so if we take it and we try to go threshold, you can then sort of drag this around and say that, you know, all of these points are clearly air, you know, from 0 and 1, but there's probably a lot of other points that are air that aren't included if we just include 0 and 1. And so where this gets all of the bone and doesn't get, or gets all of the air and doesn't get too many of the other structures is kind of arbitrary. I mean, to decide if this point is air or not is fairly difficult to say. And that's why these techniques are so important, because these images aren't perfect, which is sort of the problem we have with images in the first place. Is that when you take a temperature, you get a temperature plus or minus the standard deviation, it's very easy. And when you take an image, you have thousands and thousands of points that have sort of a huge distribution of values. And you need, for an image like this, to be able to say that this is the bone, this is the air, the average density of the bone is this, the number of cells we see inside is that, the number of vessels we have is this. And so in order to be able to make that next step, you have to be able to break the image down into something easier to understand. And so we can actually see what ISO data does. So ISO data was a little bit higher. So that's what the ISO data technique says. We can see what intermodes says. Max entropy then decides this. So maybe if you were interested in these really highly classified or calcified features, then the sort of max entropy technique would be more useful for you. You can also do in image J, I think Time has it as well, the ability to apply all of them, which I'm not sure how useful it is, but auto threshold, try all. And then you can see how each different technique with the name on the top analyze that given image. And so there's a huge variation in what can be acceptably considered calcified or what can be considered air and what can be considered bone. Because all of these techniques are developed and are existing as plugins and things because they are useful for some problem. So none of them are completely useless, but they clearly cover very, very different needs and very different types of images. And so you have to look at it and see which one works best. And ideally, you see which one works best over lots and lots of images. Because it's from one image, it doesn't give you a very good idea about things like stability or where those parameters shift. And that's particularly important for things like high content screening, where you then have hundreds and millions of images and you need to segment them all more or less the same. So yeah. So this was the auto threshold result that we see before, and so you can see all the different thresholds that you get. I think this one's different because we told it was the inverted image of what we showed before, but more or less it's the same idea. So the sort of pitfalls we have of these techniques is that they're very useful, but they can cause problems in your further analysis, and they make it, in some cases, almost too easy so that you can miss out on major problems that you have in your data. And so when we look at sort of the histogram-based approach, they're very sensitive to the distribution in your pixels in your image, and they might work really well on images with sort of equal amounts or similar amounts of each phase. So if we go back to this image we had here, reset. There's not equal amounts, but it's 3/4 bone, 1/4 air or other materials. And so that works quite well. If we take a subregion of this image, like this, and we apply an automatic threshold technique to it, then it will find something to segment in the image, even though we chose a region where there's nothing to be found. And so if you have very large samples that are very heterogeneous, where some of them might have air in them, some of them won't, and you use an automated threshold technique, it can then find objects in your image that don't actually exist because you forced it to find objects, or you forced it to differentiate your groups into two pictures, or you forced it to separate your picture into two different groups. Some of these methods have sort of a safety mechanism built in where they will fail if there aren't two peaks. So if you try to do intermodes and there's really only one peak and there's nothing else that can be found as a peak, it won't work, I think, or ISO data. One of them gives you but of course, as soon as you have enough noise or variation in your data, then it will always find something to segment. But clearly, this isn't what we're interested in segmenting in the image. We wanted this to be all white. So that's one of the major problems that can come up. The image-based ones are very sensitive to noise. And if you have large regions of your image or sort of non-homogeneous noise in your image, so if at the edges it gets much noisier than in the middle, then you can have a problem trying to optimize this entropy, and it might end up separating the center of your image from the edges. So particularly in microscopy techniques, that if you have a high illumination at the center and it's dimmer at the edges, that normally one of the things you correct for is this illumination. And so you have a constant illumination in your image, but the noise level at your edges is much higher because you have to amplify those points much more so that they have the same intensity. And finally, the results-based is sort of if you give it expectations to have. So if you tell it you want to find objects between 100 or 200 and 1,000 pixels, then it will find some threshold that gives it these objects, but this may not be meaningful for what you're trying to analyze. And if you have sort of a special case where something has 1,200 or 2,000 pixels, then it won't find that, or it might shift its approach so that it doesn't find that. And so then you can end up with really problematic images. So kind of the realistic approaches for dealing with these shortcomings is sort of the top one is really this model-based approach. And so this works, this always works if you're capable of doing it, but it requires much more time to sort of be, to have set up properly. And so this is where you try to simulate everything involved in your system. And we have some examples of this in the exercise today, I think with like a camera noise simulator, which is part of the workflow, which will sort of add noise to your system. And this then allows you to see how well you get rid of it and how well you can accurately segment your image in the presence of noise. And so if you try to look at your normal image, like we had before, where it looks like, this, you can sort of guess where the cells should be and that this is noise and that this is an important structure, but you don't know that for sure. And if you simulate your images, then you know exactly what everything should be. And so you can say that this is supposed to be a hole, this is supposed to be an artifact, this is caused by noise in the system, this is caused by everything else. And then you can apply your entire analysis chain to ensure that you get the same results out as you did, as you sort of put into the system. And one of the cool applications of this, I don't know if it was recently in MIT Technology Review, is that the people at Google making self-driving cars use video games, so sort of the Unity engine from like Unreal Tournament and those sort of games, to simulate driving scenes, and then they have their pedestrian and car detection algorithm run on these simulated movies to make sure it finds pedestrians and it finds cars under weird illumination, when it's dark, when it's bright, when pedestrians wear strange clothing, when the car moves really quickly and everything else, because you can test for millions of situations easily inside this simulated environment, and that can be much more difficult or much more dangerous to test in reality. And so this is used sort of at every scale when possible, because it's a lot easier than trying to understand your data and label everything carefully in your data, because a lot of times that's not even possible. To go through a scene of an image and circle each pedestrian and identify each car is very time consuming, and to make a video game simulation with cars and pedestrians and animals and everything else is fairly easy because someone's already developed it. The next sort of approach you can follow is a more sample-based approach. And this is where you sort of apply the methods to each sample and then keep track of which threshold was used for each sample. And then you can take these thresholds and apply them back to the other samples in the image. So you can sort of switch the thresholds around. And you can see how reliable it is on these results. And so you can sort of switch around the thresholds and ensure that your results are still somewhat meaningful when these values drift back and forth. Another approach, which is sort of the least desirable but the most time-efficient approach, is sort of the worst-case scenario. And so if you can find your images which are going to be the most challenging or difficult to segment, then you can take these images and make sure your technique gives you somewhat meaningful results on them as sort of a test, sort of like the smoke test that Anders discussed during his lecture, to make sure that your system doesn't completely blow up when you give it horrible data. So moving on to kind of the next step. So we have this image again, and we're interested in finding these canalicular structures. And so we have here sort of the main structures are easy to see, and the canalicular are sort of these small little dots there that are connected to the cells. And so they're sort of the pathway or the network for these cells communicating together. And what we want to do is we see the large structures, that they're very clearly defined, and we want to somehow identify where these canalicular are. And like we've had before, we have this histogram, and we see that this is clearly bone. This on the left side is clearly air, and that all of this in between isn't completely clear what it is. And so some of it might be air, some of it might be very thin bone or noise or artifacts in the image, And some of it is these canalicular structures that we want to extract. And so what we can do, we can then show the three phases on this image so that we see clearly where the air is, where the structures that are in between, and where the bone is. We can then use an approach called hysteresis thresholding, where we take the things that are certainly air, and so this is where we have the approach of, if it's 0 or if it's very close to 0, then we're confident that this is air. You take those pixels, and then you take the pixels and you apply some sort of morphological operation if you want. And so you can take these pixels, you can apply an opening or several openings to get rid of the small objects, and so that you just have the large groups. You can then take these between pixels and you can grow your air into them. So you can use a dilation operation on your air pixels, so the ones where you're completely confident that it's air, and grow them out into these between pixels. And so this is also very similar to the idea of region growing, if that's familiar for you. And so you have things that you're very confident are air, and if it's connected to something that's air, so these cells have canalicularly, and are connected to cells. And so you can kind of grow out from it to identify the things that are sort of relevant for what you're trying to find. And again, you sort of have this neighborhood defined, and you assume some sort of connectivity. So if you choose 6 or 26 neighbors, depends on the sort of structures you're trying to find and how well you want to fill the space, but the approach is more or less the same. And so that's what it looks like for this single image. And so here you just see that it fills up the cells well, and it finds a few of the canalicularly. I think we can take a break now, and then I'll find the image where it shows what it looks like in 3D when you apply this approach. So are there any questions on this stuff so far? Okay, so we can take a short break and then